Hi, and welcome to Chapter 9 of Computational Linear Algebra. Today we'll be looking at linear maps. So, outline of what we're going to do. We have a lot to cover today, but we're going to be going fast because a lot of this is just an extension of what we saw in 2D. So we'll be looking at linear maps in 3D, the matrices and maps that go with them, linear spaces, special cases of scalings, reflections, shears, rotations, and projections. Look at how to compute volumes in linear maps with determinants, how to combine linear maps, briefly talk a little bit about inverse matrices. Then we're going to come back and we'll give you a review of important properties of matrices, ending with what you should know in terms of our terminology. So here's a picture from the book talking about the idea of flight simulators. By now, you've all seen 3D games and computer graphics, so you understand the idea of trying to deal with a 3D world and converting it into what you're going to see in the screen. We're not going to get all the way to full 3D because we're not going to do perspective in this chapter, but we'll get through how to take a lot of this mapping stuff and make it move around. And more importantly, in the 3D model of this, you actually have to be able to map 3D to 3D to do things like move around the terrain, the clouds, and other aircrafts. So that's done through application of 3D affine and linear maps from mapping 3D to 3D. So pretty much we have the idea of our three basis vectors in 3D, right? We have a 2D space and then we add another dimension to it. So it's pretty much the same as what we saw. There's actually lots of stacks of these 2D vectors, right? Each coordinate in the 3D has a 2D subspace within it. And we're going to think of maps and vectors, which we already covered a little bit last chapter. So the idea of a 3D map then is going to be mapping from a 3D space into a 3D space. So if I have a coordinate system A1, A2, A3 with an origin at 0 and vectors A1, A2, A3, we can ask the fundamental question, what's the vector V prime in the A1, A2, A3 system correspond to the vector V in the E1, E2, E3 system? That is, we can map from the A1, A2, A3 and the E1, E2, E3 system and go back and forth. And as before, generalizing from 3D, our vector V prime is just going to be the first column of the first component of the vector times the first column of A1 plus V times A2 plus V3 times A3. So given a vector and a set of basis vectors, we can then represent it in the new space. And we can, of course, rewrite all that as a matrix equation. So we can say that V prime is equal to A times V. So V prime is our column vector. Our matrix, which are columns of the vectors we want to map them into for each of E1, E2, and E3 column vectors, and then the original data. And pretty much all the properties of linear maps from 2D carry over, and we'll talk about them at the end. Just make sure you remember them all, because on the midterm there were some issues. So if we return to the example from the previous slide, we can just rewrite that in matrix form as this 3 by 3 matrix times our 3 vector equals some new 3 vector, figuring out where it goes. And multiplication is pretty much the same. Various properties are still pretty much the same. Given a matrix, a 3 by 3 matrix, we consider it's transpose. So here this first row, which is in bold, becomes the first column. And in general, you move things by flipping them around the diagonal. So we talked about the idea of linear spaces, and in 3D, the linear space we're going to talk about in general is denoted by R3. And we associate with R3 the operations of forming linear combinations. If two vectors are in this linear space, then we can write any weighted combination of these where we multiply them by scalars R and S and add them together and get a new vector V. And this is a linear combination of V and W. And this property is called the linearity property. It's part of why they're linear spaces. Excuse me. So with arbitrary scalars S and T, we can consider the space of vectors formed by SV plus TW, the space of all of those. They form a subspace, a linear subspace of all the 3D vectors. If U1 and U2 are in this space, then they can both be represented as a linear combination using the same basis vectors V and W. And any linear combination of them can be written as alpha plus beta times each of these, which is again still in the same space. So we have a lot of the same ideas in terms of vectors that are collinear or linearly dependent. If they're not collinear, they're linearly independent. We decide collinearity in 3D now by asking, what's the dimension of the space? So if the subspace V plus W has dimension 2, it's spanned by 2 vectors. These vectors have to be non-collinear, otherwise actually if V and W were collinear, then this would be a 1D subspace. Okay, so in 3D we can have a 3D subspace, a 2D subspace, and a 1D subspace, and 0D for the zero vector. So the orthogonal projections live in the space, and we can talk about them being either linearly dependent or independent. If V1, V2, and V3 are linearly independent, then there is no solution for the coefficients of S1 and S2 to combine V1 and V2 to make V3, just like there wasn't in 2D. So the only way to express the zero vector then becomes as a linear combination of the three of them, because they're linearly independent, and you can only do a combination of the three of them to get the zero vector if S1, S2, and S3 are all equal to 0. Because they're all linearly independent, you can't combine them to get back to 0. So 3 linear independent vectors span the entire space, and they form a basis for R3. So just like 2D, we just added a third vector to make that happen. With these, we can ask questions. What is a subspace? Spanned by a couple of vectors, calculate the volume formed by them, check if the volume is 0, and we'll play some games or we'll show these in a little bit and have to deal a little bit with round-off errors. So now let's look at some special cases of matrices that would probably be pretty obvious to you. So in 2D we had a scaling matrix. Well, in 3D we have a scaling matrix as well. So if we have a matrix that is down the diagonals, S11, S22, and S33, each of those are going to scale the X, Y, and Z, or the I, J, K dimensions. And if all the scale factors are greater than 1, it enlarges things. If they're all less than 1, the vector is shrunk. And you can mix the two together, so you could have things like this, where I have one of the components is less than 1 is 1, and one is greater than 1. And what happens to this? Well, if you think about what this is doing, you can also ask then the question for this special matrix, what's this done to the volume? So if the unit cube is given by S1, so by E1, E2, E3, it's got volume 1, then after I do this transformation, you can sort of see that you can have a rectangular box whose sides are S11, S22 times S33, so the volume is just a product of those. So you can figure out volumes in the diagonal matrix very easily, just taking the product down the diagonal, which is, we've already seen, is also the product down the diagonal. We get the eigenvalues, and in a scaling matrix, the eigenvalues are the values on the diagonal, so pretty straightforward. In 2D, we talked about the action ellipse. That is the action of if I map a circle and see where it goes after the map. In 3D, we're going to do the same thing, but we're going to take the unit sphere and map it to an ellipsoid, so it's a 3D ellipsoid, and that gives us an idea. So if I have uniform scaling, then I'm going to have SII equal to 1/3, and I can have something that's smaller than the unit sphere for the non-uniform scaling. So even though these were tori shown in these drawings, you can imagine what this transformation would do to a sphere, right? It would now become an ellipsoid that's got an axis of 1/3 in the x direction, unit length in the y direction, and length of 3 in the z direction. Okay, and we're going to study this a lot more in detail when we get to the singular boundary decomposition in chapter 16 weeks from now. But overall, this action ellipsoid still gives you a good way of trying to understand what's going on. If we want to look at another special case, we can talk about a reflection matrix. And a reflection matrix is a reflection around some plane. So if I, for example, think of the plane E2, the E2 plane, the E1 plane, then I can reflect a vector around that plane. If I think about the plane E2, E3, that is the plane that contains the vectors E2 and the vectors E3, you can then reflect around that by saying, okay, that should change the sign of the first component. The sign of E1 should change, so we put a negative in front of it, and the rest of them stay the same. Now, we don't actually want to look at it just as a vector. We want to view this as a matrix operation, so we can multiply that then by the matrix of -1, 1, 1, right? It's sort of a scaling around the first axis. If we look at the second vector, if we want to do reflections around a particular line, like around the line x1 equals x3, or sorry, around the plane x1 equals x3, then what we want to do, if we want to flip around that plane, is interchange the E1 and the E3 components. So I need a matrix that when I multiply V1, V2, V3, I get V3, V2, V1. And if you think about that, you can do that with a map that has the ones down the reverse diagonal, right? Because now I'm going to take this value, when I multiply it here, it goes down there, and so on. Notice that reflections do not change volumes, but they do change the sign of the volume, so they don't change the actual volume, just the sign of it. And although here we've shown you 2, you can have reflections around any plane in 3 space that you want. You can do a reflection. Okay, in 2D, we had the special transformations called shears. We have them in 3D as well. So a shear, we're going to map a cube to a parallel pipette, and the idea is the shear maps E1 and E2 to themselves, and it's going to map E3 to some vector A3, which is AB1. So I'm going to map E1 and E2 to itself, and then I'm going to sort of take this direction on the E3 axis. I'm just going to slide it over sideways to go to some other point in 3 space. Okay, and I'm going to do that to all of space. Okay, so you can see that we do that then with a shear matrix that has got zeros on the lower diagonal, ones, and then A and B on the upper right. And notice the relationship here. I'm mapping E3 to A3, and I just basically take the identity matrix and I put in A3 down the diagonal, or sorry, down the third column associated with E3. And I can then see if I multiply that times any matrix V, I'm going to get the results being V1 plus A3 V3, V2 plus B3, B V3, and then V3. So now everything depends on V3. So in this example, we have A equals 1 and B equals 1. So as you do this, of course, you can do this not just to the things. When you do it, you warp the whole shape. So here we're just showing an example of applying that shape to a paraboloid. It's going to be sheared in the E1, E2 direction, and the E3 direction runs through the center of the paraboloid to the left. So we're going to sort of drive it over here. Same shear as we saw in the previous thing. Here we were doing it just sort of to a line, so just sort of giving you an idea what it is. But when you start doing it in 3D, you're doing it to a whole shape. So your shape becomes sheared along this direction. So now ask yourself, think if you can think of this. Let's say I want to figure out what is the map that shears E2 and E3 to themselves and also maps ABC to A00. And this kind of shear might look familiar because I'm now going to take the first column, E1, and I'm going to do something like I might do in Gaussian elimination. So I need to multiply a matrix by something that's going to drive this column to that column. So I don't just stick it in here. I have to have the shear matrix given by 1 minus B divided by A and minus C divided by A, because I need to multiply ABC to get A00. So when I multiply this column times ABC, right, for the output, you'll see that I get A times 1 plus minus B times minus B over A. So what does that give me? It gives me minus B squared over A, and then this column, when I go to the last piece, I'm going to get minus C over A. When I put all those together, I'm going to get A00. Okay? And when I multiply this vector times this matrix, I've done a shear that is the first step of Gaussian elimination. So this shear is parallel to the E2, E3 plane, gets rid of the first column, bringing them down to zeros. It's really, as you can sort of see, doing a multiplication of the first row times a constant, adding it in, and the last row times a constant, adding it in, and then it's going to get rid of those columns. So it's possible to shear in any direction. It's more common to shear parallel to the coordinate axis or coordinate plane. So just as another example, let's say I just wanted to shear parallel to the E1 axis. Okay, how would I do that? Think about that what matrix would look like. Parallel to the E1 axis means I got to keep V2 and V3 for the first element. So I'm going to have 1AB as my first row, and then the identity matrix for the rest of the matrix. And that's going to make the first row, the parallel to the E1 axis, is going to have a shearing with V2 and V3. The other two columns will be left alone. And we'll show a little bit later all shears with volume preserving, but we'll come back and show that after we get to how to compute volumes. So we can come back to another thing we've already seen, rotations, and generalize those to 3D. So if I want to rotate a vector around the E3 axis by 90 degrees to form a new vector, I'm just going to sort of take these elements on the plane and move them here. In fact, this one's very similar to the 2D matrix we saw. Why? Because you can, in fact, think about rotating in the 2D plane as rotating around the vector normal to the plane out of the paper. And so here we see that we just leave the third component alone. We leave it on the paper, and we rotate the other two axes by cosine alpha minus sine alpha, cosine alpha. So this gives us very much the same kind of thing we would see. And by just sort of thinking about how you might relabel axes, you can sort of see how easy it is to do this to other axes. If I wanted to rotate the letter L around the E3 axis, the vertical axis, I'm going to want to verify some performance, but you can sort of see I'm going to need a different matrix. So now this just looks like your standard rotation matrix, 0, minus 1, 1, 0, right? And then the other elements are just the identity part. And that'll move things around, leaving the E3 axis and rotating them around that axis. Now I can rotate around the other axis. If I want to rotate around the E2 axis, it's almost like a relabeling of the axes. You sort of leave the axis you want to rotate around alone. So you put 0, 1, 0 as the row and column for that axis. And then you do cosine alpha, sine alpha, minus sine alpha, cosine alpha. Notice the change of the sign. The negative sign for the sign is in a different location here because I have to keep this to be right-handed. Otherwise, it would be left-handed. And to rotate around the E1 axis, I just put 1 in the first row and column, and I do cosine, minus sine, sine, cosine. So this is very much like the normal matrix would look like. So if you're not sure about this, you want to do positive rotation, follow the right-hand rule. If you can remember which hand is your right hand, then you're pretty safe on this. Curl your fingers in the direction you want rotation to go, and your thumb points in the direction of the rotation axis. So if you go back up to trying to do this around the R2 axis, you'll see why the minus sign is down the other direction, because you need to rotate it. If you want the axis to go the right way, you have to put the minus sign down here. It's another example of rotation around the E1 axis. We just showed this. Now, if I want to look at this axis, I want to show we can see some very important properties of it. First of all, each column vector is of unit length. So obviously 1, 0, 0 is of unit length. To see that 0 cosine alpha, sine alpha is of 0 length, again, take the dot product with itself and you'll get 0 cosine squared alpha, sine squared alpha, and if you remember your trig identities, cosine squared plus sine squared equals 1. Same is true for this last column. So each of them is of a unit length. They're orthogonal to each other because if I take the dot product of any two of these, I get 0. So in fact, it's true in general that any rotation matrix, and it doesn't matter what axis it's rotating around, is an orthogonal orthonormal matrix. Okay, because it's orthogonal, the important properties hold that R transpose R is the identity matrix. That is, R is its own inverse. And of course that makes sense because if I rotate around any axis in space by some angle theta and then I rotate by minus the angle theta, I'm back where I started, which is what the identity matrix is all about. So that's pretty obvious. It also should be obvious that rotations don't change volumes because all you're doing is rotating stuff, and therefore they're a form of rigid body transformation. Now, in 2D, we really could only figure out how to rotate around a point, and that was a little complicated because I had to translate back to the origin, rotate, and then translate back out to that point. In 3D, we actually have a whole other degree of freedom because it's not just the coordinate axes I can rotate about. I can rotate about any arbitrary vector in space. And we're not going to derive this. The book has the formulas, but there is a formula that's pretty complicated for how to rotate around some arbitrary vector A, assuming it's a unit vector. Then you get this as your rotation matrix. I'm not going to go through the algebra there, where sines and cosines are of the angle alpha that you want to rotate the angle alpha around the vector A. And you can see this becomes pretty complicated. Turns out that you really get to this matrix by thinking about how I first rotate the vector A to some standard axis. So I'm going to rotate around each of the axes I need to get A to be a particular axis, rotate that by the angle alpha, and then undo the rotations. So you end up with effectively the product of 3 rotation matrices to get A back to a particular axis. Then you multiply by your rotation of alpha, then you go back and rotate it back. So product of 7 matrices produces this sort of complicated structure, but it turns out you can just look up this kind of formula if you know you want to rotate around some arbitrary vector. Built into many graphics libraries is just something to go compute that for you. This formula is complicated, so you can sort of check this by saying you wanted to rotate around a vector that, for example, touches the edge of this letter L. So instead of rotating around the origin, I can rotate around this, and the nice thing is if it's rotating around this, then the point that touches that line won't move. It'll be doing the right thing. You can also plug in a bunch of numbers for like known axes and see that that formula works out. So if I wanted to rotate by 90 degrees around the vector A, 0, 0, 1, okay, and I have some vector V, so I can take that vector. And because we know in advance what these numbers are, you can figure out that R for that rotation, cosine 0, sine is 1. You go back in and plug those values in, so you know the property that A1, right? A1 is 0, A2 is 0, A3 is 1. So you plug in 0 for A1, 0 for A2, 1 for A3, and 0 is for cosine and 1 for sine. And you'll sort of see that when you get back down, you're going to get the matrix you expect for rotation, 0, minus 1, 1, 0, and then 0, 0, 1, 0, 0, 1. So, and that'll rotate this vector into this. So that's just a quick check that the formula is doing the right thing. Okay, now we're going to move on to projections. In 2D, we had a nice, relatively simple process of how to compute a projection of a matrix, of anything into a line. We computed the matrix. If I wanted to project onto the line U, I just took U transpose, and that gave me a projection matrix. And these sort of parallel projections, or orthographic projections, are very useful. Note, this is not a perspective projection, which is used when we want to take the 3D world and graphics and render it onto our screen. We're not yet to that point. We're just doing orthographic projections or parallel projections. Parallel projections are idempotent maths, so we know that if we do it twice, it doesn't change anything. All that's pretty straightforward. So let's see some examples of parallel projections. So orthographic projection down the z-axis basically says I want to take the x, y, z coordinate of a point and ignore its z-axis, so I'm projecting it straight down. And I just do that with a matrix of 1, 0, 0, 0, 1, 0, 0, 0, 0. That gives me an orthographic projection. But I can also project oblique at 45 degrees and sort of project as though I put a plane over here and then projected all the things down. You can actually get this two ways. You can first rotate the space so that that plane becomes the z point and then multiply by this, so you can get these by combinations of rotations and projections to the basic axes, or I can do just what is the oblique projection. So given any particular direction, how do I compute that? Well, to construct that, it's actually a simple generalization of what we did in 2D. We're going to choose the subspace I want to project to. Either I want to project to a unit vector of a line, or I want to project to a plane that has two orthonormal vectors that describe that plane. So here we're not using point plus normal, we're using two vectors in the plane. And now I'm going to form a matrix from the vectors defining the subspace I want. So either I'm just going to take the column vector, or I'm going to take the two column vectors defining the orthonormal subspace of the plane and concatenate them. And then I'm going to build a projection matrix exactly like I did in 2D. I'm going to take this matrix and I'm going to take A transpose. Multiply those two together, that gives me a projection matrix very similar to what we did in 2D. In fact, you'll see that for 2D it's exactly the same because really we have this vector U, and we're going to take, if A is U, then we're going to have U transpose. So this is just a generalization if we want to work in 3D. So if I want to project into a plane, I can take these. I can take U1, U2 times U1 transpose, U2 transpose. Notice that I've changed the, right, when I do the transpose, I have to transpose each of the elements. If you expand that all out, you get a straightforward equation for it, and you can then see that this also satisfies that in the omnipotent process. If you want, by just doing this twice, you'll get the same values. So if I want to have a projection, as an example, compute a projection onto the E1, E2 plane, we can take E1 and E2, that is 1, 0, 0, 0, 1, 0, make a matrix out of those, take their transpose and get the product, and you'll see this gives us the matrix we saw before, which is the matrix to ignore the z-axis. And that does what we want. The projection direction, as we did in 2D, we projected perpendicular to a plane, then the kernel is the normal to that plane. If I projected to a line, then the kernel becomes the plane that is perpendicular to that line. So we have the same idea of kernels as well. Now we're going to move on to dealing with volumes. So in 3D, we don't have area, we have volume, and how you change volume when you map from 3D to 3D is a very important aspect of the action of a map. So again, if we go back to the unit cube, it has volume 1. A linear map will change the cube into a skew box spanned by the three vectors A1, A2, A3, the columns of the matrix A. So again, you're sort of seeing I map to these skew boxes and then ask the question, what's the volume spanned by A1 and A2 and A3? that volume is the volume change of the map. In 2D, the area of the parallelogram was equivalent to the determinant, and a cross product can actually be used to calculate this area by embedding it in 3D. For 3D geometry, For 3D geometry, we saw last chapter, we're going to do the scalar triple product to calculate the volume of the parallel pipette using sort of a base times area model. We're going to relook at this and look at it from the perspective of linear maps and show you another way of how we can get that. So in 2D, we knew that the area was the determinant of the transform. And in 3D, if I have a matrix, I can take the 3D determinant of the matrix as the alternating sum of 2D determinants. Saw this before. We're going to take the coefficient of A11 times the determinant of the submatrix, or the minor cofaction, minor of A22, 23, 32, 22. Change the sign for the second one, do the third one. In higher dimensions, you do this sort of as a recursive definition. You run along the row, you build a cofactor of the determinant for each piece, and so on. And hence this is called a cofactor expansion or expansion by minors. So each 2x2 determinant is a cofactor and then is paired with a change in the sign and the cofactor of the element or the minor inside of it. We already saw this last time, but just to sort of try to remember a trick to make this a little bit easier, you sort of copy the first columns. So we have A11, A21, A3, right? We're just going to replicate them in this sort of cyclic pattern. And then I'm going to go down the diagonals and subtract off the anti-diagonals. And that gives me a formula then for the determinant by just sort of taking each of these minus each of those. And that gives me the determinant for a 3x3 matrix. In 4 dimensions, I'm going to write 4 such rows. I'm going to have to replicate them farther. And I'm then going to do 4 diagonals minus 4 anti-diagonals and so on to scale this up. So if we ask what is the volume spanned by these 3 vectors, given any 3 vectors, I can ask that volume by computing the determinant of A1, A2, A3, put all these together, and this particular A1 is simple because it's got 2 zeros, so it's just going to be 4 times the determinant of the cofactors 4 minus 1.0, 4.1, multiply that and you get 3.2. We could have put 0 times whatever, but 0 times the things just disappeared, so we got rid of them. Okay, so just to make you think a little bit, what's the volume change of this transformation? Okay, again, because all these things are 0, it's going to be 1 times the cofactor expansion of this, 0, whatever. This is a shear, if you didn't recognize it, and in fact it has unit volume. It doesn't change the volume. How about this one? Again, similarly, it's a shear. It's going to have unit volume. You just march through, multiply stuff out. How about this one here? Well, this one's a little more complicated. This one is a volume changing transformation. This is scaling, but it's going to scale by 1/3 times 1 times 3, which is 1. So it's actually, even though it's a scaling the axes, the overall volume is going to stay the same. So if we want to come back and look at how 3D shears preserve volume, if I want to apply a series of shears to a matrix A that result in this upper triangular matrix, we're going to do this for Gaussian elimination, chapter 12. What we want to do is ensure that the determinant of A is A11 times A22 times A33, and that just works out because we do these cofactors and we keep multiplying stuff. When we cross them, we keep getting all these zeros, so everything disappears except for the main diagonals. And the determinant is going to be the same as the original determinant of A. So if we do that, we can go back and we get one of these kinds of shears to be able to do that. So if I want to do a very simple row operation of row 3 is equal to row 3 times minus row 2, when I go to do that kind of operation, I'm just going to subtract one row from add one row, subtracting it from another, right? Then I get a matrix going back to this example, right? I want to erase this element here. I want to make this 4 go away. I can do that by combining the rows and get this is my final answer. And you'll see that the change in area before and after is still, the determinant is still 3.2. So Shears and forward elimination provide an easy way to visualize the interpretation of the 3D determinant. They're really sort of shifting those things around. The first two column vectors of A after the transformation, A tilde, lie in the E2, E3 plane. Their determinant defines the area of the parallelogram that spans it. So if I take these two, they lie in this plane. They define a parallelogram that gives me an area, and that determinant is A11, A22. Right? Now I can ask the question, how tall is it? And the height of that box is given by the E3 component of A3. It doesn't matter what the other two components are. All that matters is I have a square base, and now I have an area on my base. Now I'm going to lift it up. That gives me the height. Okay, and that turns out to be also equivalent to the triple scalar product we saw before, because the dot product and the cross product give us those two elements. Okay, so reviewing now, we're going to go back in and start reviewing how we did the determinants. So there's these rules. If A and B are 3 by 3 matrices, we know that the determinant of A is equal to the determinant of A transpose. Doing the transpose doesn't change the determinant, doesn't change the volume. That's what we expect. Non-cyclic permutations change the sign. So if I swap rows and columns in a non-cyclic fashion, I get a minus sign. If I change them in a cyclic fashion, so if I were to do A2, A3, A1, the determinant would be the same. Multiplying by a scalar just brings the scalar out in terms, multiplying one column by a scalar just multiplies the overall area by this determinant by the scalar. Multiplying the entire matrix gives me now the cube of that scalar times the matrix. There's a couple of cases that make it easy. If A has a row of all zeros, or two identical rows, then the matrix is singular and the determinant is 0. In general, determinants don't add. The determinant of the product of two matrices, though, is the product of the determinant of the two matrices. And again, if you think about that as volume, if I first do something and it improves the volume or changes the volume by the determinant of B, followed by a transformation of A, it's the same if I do the transformations first and then apply them. Multiple rows can be added together without changing the determinant. For example, the way we do shears, because all we're doing is adding elements. We're just changing the sort of representation a little bit, but it's still got the same volume. A is considered to be invertible if it is equivalent to asking, is the determinant not equal to 0? And if it is invertible, then the determinant of the inverse is equal to the reciprocal of the determinant of the original matrix. So matrices in 3D, pretty much the same kind of properties. We have this new idea of these cyclic permutations because we didn't have those in 2D. And pretty much everything else, in the cube for the overall scaling of the matrix. In doing this, just to make sure you remember that there were some issues in the midterm, that everybody got all the linear stuff right. So if I want to apply a map A to a vector and a map B to a vector, I do multiplication. I can actually multiply the matrices together. And again, in tableau form, it's pretty simple. We're going to take A, here we have B times A to give C. So we take the column of, the row of B times a column of A, and it gives us the point of intersection where they come together. And as before, we can multiply two matrices together in general if they're M times N times P. The inside dimensions have to match, and then we get an M by P outside dimension. And so for 3D transformations, we'll generally have a 3D matrix times a 3D matrix. But when I'm applying to shapes, I can have a 3D shape times, which might have a lot of points in it, times a 3D by 3 matrix to get the transformation. Just as in 2D, matrix multiplication doesn't generally commute. Again, think of that in terms of rotations. If I first rotate L up this way and then down, that's very different than if I first rotate it around this axis and then up. Okay, it changes very much, depends which ones you apply first. For rotations, right, we can just talk about the product of two rotation matrices. That gives us the combined rotation. And again, this shows the non-commutativity we just saw in the previous graph. Inverses for 3D. Inverses undo linear maps. So definition, which many people didn't get on the midterm, is that A times its inverse is equal to the identity matrix. Doesn't really matter which of the order you put it in. So A times A prime gives me back the identity in either order. It's doing the opposite of what the matrix does. as long as the matrix is invertible. If the matrix is not invertible, then I can't have an inverse and I can't get back to the identity matrix. For example, projections. If I go from 3D down to 2D, I can't go back up because I've thrown away too much information. Or orthogonal matrices are a very special case. They have their transpose is equal to their inverse, and a lot of people were confused about this as well. Only orthogonal matrices have that property. And for them, forming the inverse is trivial. It's just no real computation. You see the transpose. And for example, for rotations, that's true. It's also true for reflections, because if I first reflect around a plane and then reflect back, I'm back where I'm going to be. This provides a lot of savings in graphics where we rotate a lot or do reflections, and we have to deal with them. Just as in 2D, for 3D, scaling matrices are particularly easy to compute the inverse of. A diagonal matrix, we just take 1 over each of the diagonal elements, and that gives us the inverse of that. Okay, so summarizing, we're now going to start going back through a bunch of the rules. A couple of things for inverses. If I want to take the nth power of the inverse, that's the same as saying I want to take the inverse and then multiply it by itself n times. With the special property that A's inverse is back to A. If I want to scale everything by a constant, if I take k times A and ask for its inverse, it's 1 over k times the inverse. And if I take two matrices and I multiply them and then ask for the inverse, it's the same as taking the inverse of the second matrix times the inverse. Note, when I take the inverse, I swap the order when I take them out of the product. And we'll talk a lot more about this when we get more to Gaussian elimination and other ways of computing inverses in higher dimensions. Unlike 2D, there's no simple formula to easily write down and use in high dimensions. So going back on, reviewing a bunch of matrix properties, restating some of those that hold for n by n matrices as well. Matrices preserve scaling. A times a scaled vector CV, is the same as that scaling C times A times V. They preserve summation, so I can do combinations. A over product is distributed. They preserve linear combinations. A times a weighted combination vector gives me the weighted combination of the properties. Overall, I have the distributive law. A plus V, AV plus BV is equal to A plus B times V for matrices. For commutative law, I can change the order. A plus B and B plus A works for addition, does not work for multiplication. We have an associative law for addition. I can associate them, and association works for multiplication. For distributive laws, we're now going to distribute multiplication over addition, and that works as well. Doesn't matter what order I do it in either. Our basic scalars, if I multiply by a scalar, again, this comes back to the basic properties from it being linear. The scalars can be multiplied before or afterwards. They can be added before or afterwards, and we keep all of the right properties. And when we're playing with determinants, we have to be a little more careful. The determinant of A is the same as its transpose. The determinant of matrix A times B is the determinant of A times the determinant of B, but they don't add. So the determinant of A plus B, the determinant of B, is not equal to the determinant of A plus B. And if I multiply by a scalar, so scalar laws for matrices are okay, but for the determinants, if I multiply a matrix by a scalar, I get the nth power in n dimensions of that scalar times the matrix itself, the determinant of the matrix. Looking at just the transpose, we have some other things. We have A plus B transpose is equal to A transpose plus B transpose. The transpose of the transpose is the original matrix. Multiplying by a constant doesn't change anything. But when I take the product of A, B transposed, I get B transpose, A transpose. That order swaps out. And in terms of exponentiation or products, if I say A to the R, I really mean A times A R times. Clearly to do that, because I have to have A in the middle here, A better be square because I need it to be able to be used in all those multiplications. Overall properties, if I do A times raised to the power R plus S, that's the same as A times R, A to the R times A to the S. In fact, you can recursively decompose A to the R. A times the power R to the S is A times R repeated S times, so it's A to the R to the S. And we have a special case that A to the 0 is equal to the identity matrix. So this is a special case. You can't write it out R times. You don't write it out at all. It's just, this is a rule you're given. So for this chapter, there's a bunch of terminology. Most of it is relatively straightforward extensions, but you should now be able to talk about those extensions in 3-space for things like linear combination, linearly independent. Again, it's still like the number for a matrix, the rank is still there. We talk about orthographic projections, cofactor expansion. You should know all these terms. Not part of the extra credit, but you might still want to write down all these and write your definitions down to help you remember these words. I don't have any examples here from the end of the chapter for you to go over questions. I strongly encourage you, we'll be going over clickers in class, go through some of the problems at the end of the chapter, review those problems. Again, half of them have answers in the back of the book, so try and work through 1 or 2 of them and then work on those.